I'm Alex Miller. I'm here to talk about the joy of data. I've been a member of the Clojure core team since 2013. I've been at Nubank since 2020, where I work on the Clojure team here. I've been the former organizer of lots of conferences, Strange Loop, Lambda Jam, Clojure West, Clojure Conj, and trying to get out of that business. But I'm also the co-author of several Clojure books. If you're interested in programming in Clojure, I would say don't buy it, because the 4th edition is coming in a couple weeks in beta edition. But you should buy the other ones. Clojure Brain Teasers is a new book that just came out this year, and I think it's particularly will be good if you're a new Clojure developer. So it's a good companion to some other introductory text, whether it's programming Clojure or Clojure for the brave and true or getting Clojure, any of the or living Clojure, all those are good. So we're going to talk about data today. So we have to start with the dictionary definition, as I think I'm required by Rich to do that. So data is a plural noun of datum, which is, we'll say, a collection of discrete or continuous values that convey information, or things that are known or assumed as facts, making the basis of reasoning or calculation. So it's at the basis of what we do as programmers, right? And interestingly, it's from the Latin participle datus, which means something that's given or offered or yielded, or if you use it as a noun, it is a gift. And I will say that data is a gift. So I think that's a good thing to think about. Something that people have given to you, and you should treat it respectfully. So we're going to talk a lot about values. So what is a value? So it's a little hard to pin down, especially without using the word value. But it's often some numerical amount, some magnitude or quantity or number. Like we could say, you know, the number 52 or something is obviously a value to us. It can also be something that is of relative worth. It is of value to us. And it could also be the sort of properties of a thing by which it's rendered useful. So it has properties that make it useful to us and is therefore valuable, right? So these are some example values. These are not all Clojure syntax necessarily. They're just trying to talk about things generally. So I think we could all easily agree that numbers are values. It's like especially in computers, that's the obvious thing. We've got some representation of numbers. Booleans are also, I think, clearly values for us. Individual characters, that actually gets a little murky once you start to look into multi-byte Unicode characters and things like, you know, UTF-16 and surrogate pairs and all those kinds of things. But I think we should easily want characters to be values and independent things. What about strings? So like, strings start to get a little more interesting. Like, it's made up of characters. So if a character is a value, is a string that's a composite of things a value? And if you look at older programming languages, they were not values. They were mutable things. But these days, most programming languages treat whole strings as values, individual values. And I think we should be thankful that that's true. You can think about UUIDs. That's maybe an interesting sort of abstract kind of a value. You know, you pick up this random UUID out that's not changing or anything. It's just a thing that we rely on for identity, right? And then thinking about collections. If you've got an array of Booleans or a map of strings to numbers, like, are those values? Like, I think what we're going to say here is that we want those to be values. So we want aggregates to be values too. So what do these values share? What makes them? What are their properties that are useful to us? They're immutable. Like if we have the number 100 somewhere in our programming language, it doesn't magically change to 50. When you come back and look at it later, it is always there, the same value. They're comparable. You can take two different values and compare them and decide if they're the same value or if one is bigger or less than the other. You can sort them. That's a really important property for us. They're shareable. You can take that value and convey it to another thread in your program, or you can convey it to another person or another program that you're sending it over the wire to, or you can write it down on disk and read it back. And it's still going to be the same value, right? And they're precise. To do all these things, they have to be ultimately representable as some bits that are sitting there in your memory or on your disk or wherever. And that allows us to do things like compare them. So for us as Clojurists, we feel really strongly that aggregates of values are also values. And this is not true in other languages. So this is like an important point of differentiation. If you've got a Java util array list in Java and you put strings in it, that's a mutable collection. So it can be changed. Somebody can take the thing at index 5 and change it from 100 to 50 to 20 or whatever. So that is not true in Clojure. All of the Clojure collections are immutable and comparable and shareable and precise. Those things are all true of collections as well. And there's really only a handful of really common collection types. There are lots of different data structures. There are lots of exotic things people have come up with. But really, like when you come down to it, there's only a handful of kinds of things that we use all the time. And if you look at JSON, JSON just has like objects and arrays, right? Like you got two kinds. And that's actually covering the 90% use case of what you need. Also interesting to think about is what are not values. So objects, mutable objects are not values. They are not immutable. You can change things in them. They might have hidden state. You might have a difficulty conveying that over the wire or sending it to, or writing it down or conveying it to another person. Interfaces are not values. They're just a description of behavior. You can't send an interface over the wire, right? You have to send something that has data in it. Files are something that's sitting on disk and they can change externally, right? They're mutable externally. So the files are definitely not. But what about paths in a file system? Maybe. Like you can actually, in Java, you can treat paths as immutable abstract things. That's actually pretty useful. So paths are kind of can be a good value. There's a lot of special cases around things like dot and relative paths and things like that. But within some constraints, you could probably see paths as values. Things like sockets obviously have this underlying network community. They're holding on to resources in your operating system. Those are not values. You can't write those down. You can't compare them necessarily. You might be able to compare identifiers for them, like a file descriptor, but you can't compare the sockets themselves. That doesn't make sense, right? Things like streams and iterators are interesting. They are things that are consumed as you read them, right? You're doing next to walk through a stream or walk through an iterator, things like that. So those are definitely not values. And there's many other things. So I'm going to talk a little bit about Clojure. And this hopefully is review for most of you at this point. If you attended the workshop yesterday, you've been seeing things today. So I'm not going to belabor it too much. But in Clojure, we really primarily deal only with values, and that includes collections. So collections are values. They are precise and immutable and have all those same properties that individual values have as well. So the four main primary collection types in Clojure are lists, which are sequential, not indexed, and you add values at the front. Vectors, which are sequential but indexed, so you can look up the value at some index in the vector, and you append at the end. Maps, which are key value mappings, and they're unordered. And sets, which are also unordered. You can only have one of each thing in there, at most one, and you can easily check for containment. So all Clojure values are immutable, including collections. So what are the consequences of that? You can read the value without asking. If it's immutable, nobody else can change it. You don't need to take a lock or ask anybody to look at it. You can always read that without asking. You can freely share it to somebody else, to some other thread in your program, or you can send it to another program. That's fine. Nothing's going to happen to the value you have. It's immutable, right? So you can easily share it to other people. You can write it down and read it back. we've said that it's precise, right? And there is some precise representation. There might actually be multiple ways to represent that as you serialize it out to someplace, but you can write it down, read it back, and be confident that you have all of the semantic information that you had to start with. You can remember it and reuse it. Since it's immutable, like, it's great for caching. It's perfect for caching. If you were at the Datomic workshop yesterday, like, Datomic is just built on a tower of caches because it's all immutable. It's great. You can undo or time travel through different versions of your data. If you are always moving from one immutable value to another, then you can keep a hold of the old ones. Like, that's fine. You can go back to the old one without seeing any changes that happened since then, because those were different versions of immutable values. These are awesome properties. They're not free. You have to pay for them a little bit in performance, but it's so worth it. So that's my big takeaway of doing Clojure for a long time, is that immutability is definitely worth the price that you pay for it. So let's look at those properties a little bit more in depth. Comparison by value. So when you compare two individual values, two numbers, for example, they both have some precise representation. They're being stored in some number of bits, and you can just compare those bits. And for a lot of important types that we deal with, that stuff has hardware level support, so it's super fast, right? There are some special cases around those things. So if you look at, IEEE 754 floating point spec, there's several different ways to represent 0. Sometimes you want -0 to equal 0 to equal 0.00, and sometimes you don't. So there are some funny little cases in there of things like that. But in general, most of the things we deal with have these precise representations, and they're easy to compare. So how do we compare aggregates, these collections like that? In general, all of them, if you're comparing two collections, they must be the same size. If they're not the same size, they can't possibly be the same collection, right? Lists and vectors are generally equal if each element in the collection is equal to the other collection, and they're in the same order, right? And if you go look at the places where this stuff is defined inside Clojure, they read almost exactly like these descriptions. So maps are equal if the two maps have the same keys and if each key maps to the same value. And you'll note that I did not say in order here, because these are unordered collections. So you need to look at each of the keys, but you don't care about that. There is no order that's defined. And sets are simply equal if they contain the same elements. And again, order is not important here. Names. So Juan was talking in the last talk about names a lot. He did a great job. I'm going to mostly say things that he just said. So I'll say it again, and maybe hopefully it'll sink in even more. Inevitably, you need some way to name values or to name parts of values. And we have these two things in Clojure, symbols and keywords. And symbols, like user or plus, is a name that refers to something else, giving it identity. An evaluation yields the reference thing. So keywords like name or email, :name or :email, these are names that refer only to themselves. And so they're really ideal enumerated values. They're just like, here is a value, and I can use that, and it doesn't ever mean anything else. It means that. And so it's great for naming parts of a data structure or naming keys in a data structure, things like that. So when you evaluate, it yields itself. And in Clojure, it's implemented by actually literally every time you refer to :name in your program, it's pointing to the exact same object. So it's very memory efficient too. If you've got a map that has 100 different, or a list that has 100 maps in it that all use the same key, you're using one keyword for all those things. So it's very memory efficient. So what do you think? Are keywords values? I only see a few hands. Are keywords values? Yes. More hands. Yes. Definitely. Keywords are definitely values. They're precise. They're immutable. They only refer to themselves. To me, that's just like a clear thing. What about symbols? Are symbols values? Who thinks symbols are values? So I'm not going to penalize you. Who thinks symbols are not values? Okay, more hands in that one. So I think it is. You can get a little more fine-grained. It is confusing. I think this is truly a confusing point. And I sat and thought about this for a while. Like, it's not, I don't think it's an obvious answer to this question. I would say that quoted symbols are values. So when you're talking just about the symbol itself, by itself, that symbol is an immutable, precise thing in Clojure. But when you start to bring in evaluation and in the meaning, in the context of Clojure expressions, so an unevaluated symbol is going to get evaluated to be something else. And because of that, I would say it's not a value in that sense. So this is kind of, I'm splitting some hairs here. This is kind of it's difficult to talk about. And both of these can be qualified by namespaces, giving it more context. And Juan was talking about this a lot, and I really appreciate all the things he was talking about. And I kind of want to see the rest of his talk, actually. I was kind of curious where he was going with all that. But I'll expand on it a little bit since it was brought up. So the basic idea here is that names are great. It's great to call something a name or user or balance or whatever. But that, there's only so many words, right? We can't use the same word all over the place. We can't have, the user's email and the company's email and then, some other kind of email. So you need some way to talk about names in context. And so that's what the namespace system does, is it gives you an ability to use arbitrary amounts of context to narrow the scope of what this name actually means. And we do a lot of things in Clojure, like aliasing, to allow you to, or the double colon auto-resolved keywords. Those are ways to allow you to mean a big name, but say a short name, right? So that just physically we can type fewer characters to say that. And we've got all kinds of different tools in Clojure to do that, which is just a convenience for us as programmers, right? And sometimes, like, the scope of what you care about is inside a method. And in that case, you don't need to give it a name that's got, like, 10 namespaces on it or whatever. Like, just being inside the scope of a function, that's sufficient. Like, it's scoped to that function. Like, I don't need to say anything more specific than that. But we have this whole namespace system, which was inspired by Java's package system, which uses a sort of reverse domain name system, is where it started. So you take something that you control, the domain name or possibly a trademark or something like that, and use that at the front of the namespace hierarchy. And then you use ever progressively more narrow scopes to give yourself a name and context. And the beauty of that system is we can live in a global world where we all control top-level things and agree on what we mean inside that narrower scope. And that means that we can have one spec registry and put stuff in it from libraries and applications and like all kinds of different places, and they don't conflict. So if you always call your things, :user/name, then you're going to conflict with somebody else who's doing that. But if you call yourself, Nubank accounting.user/name or something like that, you have way more context. So that's just going off on, and the other aspect of it is in terms of overlapping with the var system. So we have this natural hierarchy inside Clojure of vars. So vars live in namespaces. Namespaces use this context. So you have a full tree of names that is built into Clojure. And the tendency that people take is to just put more stuff on vars, add more metadata onto the var to describe more things. And the point Rich was making when he talks about spec is we don't have to put everything on vars. You can use the exact same naming system and put them in a map. And any map you make about any topic, you can use that. So like spec uses its own map, the registry, to define spec definitions. As opposed to other schema libraries, like schema in particular uses vars, and I think maybe Molly uses vars too. I'm not really, can use vars, I'm not sure. But so that was the point that he was trying to make there. And then I'm not going to go too deeply into this, but I do think it's a really important aspect of Clojure's approach to values and data is that we have this sort of uniform and universal access language to talk about the insides of our collections. So when you're in an object-oriented system and you need to talk about how to get to the fields inside there. Like, just think about what we do, and like, I don't know how many people are familiar with Java or other object-oriented languages, but that's where I've spent the majority of my career, other than Clojure. But like, you put your data in fields inside classes, and those fields, we make them private and put getter methods around them because they're not immutable, right? So because they're not immutable, you have to protect them with accessors, and you might have to put locks and things like that around protecting them. So like, this is the first consequence of mutability, is protection. Like, you have to protect yourself against other people changing your stuff. And then once you do that, then you've created a get first name, get last name, get email, and you've created this whole new like set of language. In every single class, we're creating a new special language to talk about that new type. And so Clojure, like the consequences of having this everything be immutable and everything be in a handful of simple collections, is that we can use one simple like set of functions to get at the data inside of those, and we never write a get name or whatever. We just have these generic things that we can use to look at all the data that we have. And that's what makes Clojure feel like it makes your data feel really accessible. It's like that, plus the literal collections means you can just write these things directly without having to go through, mutators and methods and things like that. And then you can get the data out because it's all just right there, and you use the exact same functions every time you want to go look up something inside the collection. So all of the collections in Clojure support count, which gives you back the size of the data structure, and seek, which gives you a sequential view of the data, and that is the gateway into using this whole library of sequence functions that are available to do all kinds of different things. But I'm not even going to talk about, but like, we can treat everything as a sequential view, and we have this huge library of sequential functions. And the combination of those two means that you get a ton of reuse. Like in OO, I did Java and OO for many years, and it felt like you were always promised that like reusability of objects was like the holy grail of things, and I never saw it. Like, you were always creating new classes every time you did anything, and you were creating lots of them. Whereas in Clojure, like, you create just a handful of collection types, you convert them to sequences using this one function, and then you can use this huge library of functions. Once I know how to use map and filter and keep and remove and all that, like, it works on anything, right? It's like, that's huge power. Like, you do not have to learn these custom interfaces every time. So that's great. Index data structures use inth to look up the value at an index. Associative data structures like maps and vectors use contains to check for containment, and you use get to look up a value at a key. You use find to look up key value pairs, and keys and vals give you back all the keys or all the vals, which is great for discoverability, right? We can easily figure out how to write that down in a file because we just go to keys and vals, and you can write, or you can use a seek and walk through them all. One interesting property that it's good to know about is that seek and keys and vals are all guaranteed to give you back each of those things in the same order for any collection. So like, you can rely on keys and values matching up. So you can split them apart into keys and vals and then zip them back together if you need to. So that's uniform access. And then we haven't talked about functions at all yet, really, but so most Clojure functions are written to take values as arguments and return a value as a result. So we've already got this like really stable, infrastructure to build on, all these immutable values that aren't changing. And then most Clojure functions are, again, just literally mathematically functions of the inputs to the output. So why is that good? It's predictable. It's very easy to reason about, to test and debug. It's composable. You can take multiple functions that are pure functions working on immutable values, put them together and make a bigger function, and it still has those same properties. Like, that's huge to get that. If it's safe for concurrency, because we know that if we're just working on immutable values and you can do that in your own thread, you're not having any side effects or hurting anybody else. You're not modifying anything anybody else cares about. So you don't need a lock, you don't need to worry about that stuff. It just removes a whole class of problems. it's stable. It's easy to evolve and refactor because adding new features to your system often means adding new keys to a map. And that means that the existing code, using the existing keys, nothing has changed, right? Like you can add new paths through your system without necessarily changing anything about the existing system. And I'm sure some people have seen the sort of the layer cake pictures for Clojure of like the stability of Clojure over time. I forgot to put that in here, but like Clojure itself has been mostly additive over time. So we're not really like, changing existing code, we're adding new code, and very few changes need to happen to new code. So that makes systems really stable over time. So this is the key slide. If you're going to remember one slide of this whole talk, this is it. So there is a very simple algorithm for solving problems in Clojure, which is represent your domain as data, write functions that transform and manipulate that data, and that's the end. Like, that's the end of the story. And if you can rely on these just data and functions, like, you are winning. So that is my summary. I'm not done, but that's my summary. So keep that in mind as we go. Okay, I have some examples now, so I'm going to move a little bit here. All right. Good. That's good. Check one? All right, that's good. All right, we're just going to go through a series of examples, try to drive this point home just until you're sick of it. So say you've got a to-do list. You want to represent a to-do item as data. You can just treat it as a map that's got some keys in it that says, one of my to-do list items is just, I got to do an errand, which is to get groceries, and I think it's going to take about 60 minutes, right? And you might say, well, that's a lot of things to type to say that, right? And sure, that's great. We have functions. So, write yourself a function that takes those three things and gives you a more concise way to say those three things together. And so I'm over here on the right side of the slide. That's kind of what I'm doing, is just using that function. You could even go farther than that and write a macro that lets you use interpret some data structure in a more concise way. So there are lots of tools for saying things more concisely in Clojure, but at the bottom, you should have data that is just, and often it's maps. So I don't know how many people were paying attention today, but in almost every talk today, somebody has shown a picture of a map to represent the core data of the thing they're talking about. We saw it with Sandra's talk, we saw it with Juan's talk, we saw it. So we've seen, and Alex's talk, all those talks had examples of this out there today. And that's because that's how we do things in Clojure. This is it. You can, then you might want to convert this stuff into HTML, for example. Like, I'm writing a web app now. I want to convert it to HTML. We've got a great library in Clojure called Hiccup that has a very concise data representation that knows how to convert data structures into HTML. And so I've broken this into two functions. In general, I would recommend using lots of small functions. It's not uncommon to look at a Clojure code base and see that the average size of a function is 5 lines. Like, that's a pretty typical average. You will have functions that are 10, 15 lines long, but those are much less common than the 1 and 2 and 5 line functions that are out there. And it's definitely worth breaking those things into pieces. And this is a really common pattern that I have here, which is if you've got a collection of things, write a function to deal with one thing. It's really easy to figure out exactly what you're doing with that one thing and to test it, and then write a thing to deal with the end things and call the last function. So that's exactly what's happening here. We're using to-do to HTML to return a Hiccup data structure from a to-do item, and then the to-dos to HTML is going to basically take a collection of to-do items. It's going to map through them and call to-do HTML on each of those, and then combine those into some greater structure. So I'm going to switch over and show some actual code here. load that up. I'm using an IntelliJ with cursive right now, but you can use anything for this. I've used lots of different editors in my time as a Clojurist. All right, and we could just check what happens here if we call this. This might be a little hard to see, but I could zoom in a little. So you can see that I'm actually getting this todos.html is returning just a big HTML string out of it, right? And then I've got a helper here to just pop that into a browser, in case you don't believe me. So we've just taken that and just converted it into some HTML. So that's one simple example. That's just in case things didn't work. So I've done this before. So some takeaways here. You can have verbose representations as map, and I would encourage you to start with that. Even if you write lots of more concise things later, start with that. Always have a bottom data layer that bottoms out in verbose maps. You'll thank me later. And you can manipulate those with data functions. You can construct them with data functions. And then you can write libraries to provide helpful macros for that kind of stuff. There's all kinds of tricks you can play with doing that. That's its own art. But at the bottom, you're really going to want the maps. Conway's Game of Life. People have probably seen Conway's Game of Life before. It's a grid with cells. Every cell is either alive, where it's on, or dead, where it's off. And you figure out what the cell is going to be next turn based on the current turn, which says basically either it's alive now and it has 2 neighbors, or it has 3 neighbors that are alive. So that's kind of the simple rule for Game of Life. One of the common patterns that you see with that is called a blinker, which is just something that's all on, and then it switches to all off. And you can go work through all the logic on each of those things to see how that works if you want to, but I'm not going to bother doing that. So how would we represent life as data? So there are many ways to do this. You can find lots of examples out there online, but one of the simplest is just to represent a cell as a column and the row in the grid, and then to think of your sort of world or your grid as the set of cells that are currently on. So this is a sparse representation. I'm not making a big array of arrays and finding, putting 0 or 1 in each of them. I'm instead just remembering the ones that are on right now. So this is a full implementation just on the left side here of the Game of Life in Clojure. Clojure is very concise. I can fit it all on a slide. I actually probably could have done it a little more concisely even, but I was trying to make it readable too. So we've got some helper functions here. Like I said, it's great to break these things up into little helper functions. The first one just figures out what are the coordinates of all the neighbors of a cell. So that's all it does. And the second one is implements that liveness rule. So in as concise a way, I got it into one line, basically, of implementing that rule. Either the number of neighbors that are on is 3, or the number of neighbors that are on is 2, and you're currently alive. And so you have to get that information from somewhere. So there's this step function that's each step of the world. So you start with some initial world, and you're going to then thread this world through a series of functions. And each of these steps will do, one individual things. And you'll find this pattern of writing a main function that threads work through a series of pipeline steps is extremely common in Clojure. And every one of those steps is usually immutable data that's passing through each step. And you've got these individual pieces that sometimes are so simple that they're solved by the core library, right? And I'm using things like frequencies here and mapcat, and so I'm using functions just out of the core library. And then you might need to call into some other helper functions that are in your domain. Things like here where I'm filtering the live function to figure out which of the cells that I found are actually alive in the next turn. So that's an extremely common pattern. And then life at the end, I'm just using iterate, which again is a function in the core library that says keep calling the function step, in this case, starting from an initial world. And this actually gives me an infinite sequence of all of the future states of the world. So I've solved this Game of Life for this starting pattern for the rest of time. But it takes a long time to print out all of those. So instead we just take 4 of them in the example here. We don't have time to print out an infinite sequence. So I can just show you that. I didn't actually build a GUI version of this for this particular example, but I have done that in the past. It's not too bad. So you can see here, this is the blinker pattern. We're just starting from an initial world. We're running live, taking 4, and then I'm using pprint from the Clojure core library. And you can see that it's, if you look, that it's all the column 1 and all the row 1. It's just flipping back and forth. So that's just a simple game of life. I like it because it's so concise. So some takeaways here: focus on simple data, use small, pure functions, and you can test each of those individual steps in just isolated pieces. And I would encourage you to do that with, like yesterday when we were in the Clojure workshop, set up a connected REPL, learn 3 or 4 structured editing commands, work in your editor in a file, and evaluate small pieces as you go, test small pieces as you go, and then transfer them into unit tests as you need. That's a super strong pattern. That's where you really start to get the flow state of working with Clojure. I'm going to skip through a couple of these a little faster for timing. So how do we represent dependencies as data? So this is from a library called toolsteps, which I wrote. And that's at the heart of Clojure, the Clojure CLI. And it's really, we might need some way to represent dependencies or as a map of libraries. And there are some optional attributes in here to do things like point to parents in the map. And so inside Clojure tool steps, we will actually build a tree of dependencies. Really, it's a graph of who depends on what. And then you can easily then take that information and draw a graph out of it. I'm not going to run this, but you can just basically turn that into, a graph. And this is from another library called toolsteps graph that takes toolsteps trees and turns them into graphs. So this is a useful tool you can run from your command line. You can represent graphics as data, right? You can circles, X, Y, radius, color, things like that. And then if we do that, we can draw random circles. Built into the JDK is Java 2D. There's a great library called Clojure 2D that wraps that and makes it just a little more palatable for us to run from Clojure. This is the whole program for just drawing some random circles on the screen. So that's kind of a fun thing to do. So we can go here, draw some circles. Like, where is it? There it is. I'm gonna put this down here. I'm gonna get our interpreter in the circles. I wanted to do that all day. So that's an easy way to do some things. And we can even represent music as data, right? We can just imagine, and this is actually an example that's extended a little bit more in programming Clojure. If you look at that. Oh yeah, thank you. So we're going to represent music as data. So you've got some pitch in some particular octave that you're going to play for some length of time at some volume. Like that's enough to talk MIDI basically to some sort of MIDI output. And you can think about this, kind of interesting thing about rests. What do rests share with us? Rests have a duration, but they don't actually have a pitch or a volume, right? So you can think of as a rest as just something with fewer attributes. And that's actually really powerful in Clojure, is since you don't have to define all these required fields, you can just omit fields and maybe get something that's still useful. And you can combine those into a song. So this is just aggregating up into bigger collections. And you can easily write this with some helpers. And built into the JDK is actually a MIDI synthesizer. So that's great. We can do this just straight from the JDK without any additional libraries. And this is the code, which is not too long. So we're going to see if we can get this to work. So if anybody remembers from a million years ago, the Close Encounters theme. Try to do that. Now is the test. Yeah. Okay. Right. Yeah. So that's cool. Working. Get a little ominous. All right. So That's easy to do. You go play around with that. If you really want to play around with music on Clojure, though, the right way to go is Overtone. So Overtone is a fantastic library that's a front end for a program called Super Collider, which is a sound server, and you can do people do full live music performances with it. I am not that talented, but it's a fantastic thing to use. So I mentioned the model optional attributes. That's a useful thing. And I want to mention a couple other things. I'm almost done. So metadata is data about data, does not influence equality or comparison. It's really useful for things like annotation, provenance, type hints. So here I'm annotating the song with the composer in a metadata map. And what else? So much else. Like everything in Clojure works this way. And it all works together. It's awesome. So these are some examples of other things. You might say, but my values actually do need to change over time. Cool, we've got you there too. So that is state, and you want to create some stable logical identity that's going to have different immutable values over time. And Clojure provides these stateful constructs, things like atoms, refs, and agents. We change by providing a function to the stateful construct, and that allows us to not fight and not have to lock. Read is always available. That's one of the big pros. And users don't do locking themselves. You basically are relying on Clojure to handle and take care of that stuff for yourself. And we do have coordinated reference types with software transactional memory. It's shocking that we almost never use them. So that was not obvious when Rich started Clojure, but it's something we have observed over time, is you can get by with an amazingly little amount of state in your system. So to wrap up, Clojure provides a simpler way to think about programming based on immutable values, pure functions, state only when you need it, and this approach is simple, easy to understand, growable over time, safe for concurrency. You're really building on bedrock instead of building on sand. It is, in my opinion, the only way we should be writing programs. So data and functions equals winning.